Hey, welcome. This is going to be the second part, or kind of the sequel to the previous video on chain rule case one. This now we'll go over case two. So again, I'll just read the statement, but it's pretty similar. So suppose that z equal to f of xy is a differentiable function of x and y, where this time x is a function of g and y is a function of h, but both both g and h are functions of s and t, or have s and t as their dependent variables. So yeah. In this case, yeah, and they're both differentiable functions of s and t. If we have that kind of condition satisfied, we then also have this right over here. And this time, this is where your dependence trees are going to be much more important. And in this case, we will always be using partials or partial derivatives because in this case, there are just those multiple cases, whereas in the first one, there's only that one dependency on t. Okay, so the way we want to conceptualize this or think about this part here, at least, is as follows. So yeah, again, as before, I'll just draw out the tree and then we'll go into the actual question. So here, z, or c, whatever you want to call it, again, is a function of x and y. But what's here, I'll actually draw these bigger so we have more space to work with. So again, z or f, they depend on x and y. But here, what's different now is x and y, they both depend on s and t. So previously, we had this kind of one branch case where, or we still have two branches now, but it's slightly different in this sense. So we'll now do the same thing with the branching. So we'll go down again these different branches. So here at this step, we still have partial z, partial x. Once we get over here, notice we have two paths now, which is why instead of using like dx dt like we did before, we now need to use partials. So here we have partial x, partial s. Here we have partial s, partial x, partial t. And then similarly on the right branch, we have partial z, partial y. And then here we have partial y, partial s, and then partial y, partial t. So if you follow the same kind of dependency branching situation, you can get exactly these equations. So for example, for partial z, partial s, you're looking for all paths that eventually get you to partial s. So in that case here, we see one case over here. And then here we see one case over here. And that's again where we get this, right? So here you have dz, dx. Yeah, dz, dx, and then here you have dx, ds, which is right over here, or partials. And then over here, you have partial z, partial y. And then you get partial y, partial s, which gets you exactly that path. And you can repeat the same thing for this case over here. Okay, very good. I'll move this over here for now. Okay. So now the question, I'm going to go over a quick example. So if z is equal to e to the x times sine y, where x is equal to st squared and y is equal to s squared t, we want to find partial z, partial s, and partial z, partial t. So let's get into that. Okay, first we'll go for partial z, partial s. As I always recommend, write out the formula first. So for partial z, partial s, we have the following. Partial z, partial x times partial x, partial s plus partial z, partial y times partial y, partial s. Right, so again, exactly this over here. And then now we can just compute each one of these partial derivatives individually. So partial z, partial x, again, I'll just write over here, partial z, partial x. Z here is e to the x sine y. Again, we're treating x as a variable, so sine y is effectively a constant. So in this case, it's just itself is e to the x derivative. The derivative of e to the x is just e to the x. So we have e to the x sine y, and then partial x, partial s. I'll actually just write here, so it's convenient to see partial x, partial s. So here, again, we're looking at, move that over. So we're looking over here and we're taking the partial derivative of this with respect to s. So again, you treat s as a variable, meaning this is just equal to t squared. And then similarly for partial z, partial y, we'll do these same computations. Actually, let's find this. I'll just move here for now. Yeah, that works. Okay. So similar idea for partial z, partial y. Here, you're just taking the derivative with respect to y now. So e to the x is effectively a constant. Derivative of sine is cosine. So you have e to the x cos y. And then you have partial y, partial s. Which in this case, looking over here, we're taking the derivative of this now with respect to s, where s is a variable, t is a constant. So this gives you 2st. Very good. And now we can just put everything together. So I'll actually move this a bit down. Okay, partial z, partial x, we have is e to the x sine y. Partial x, partial s is just t squared. In this case, you didn't really need the brackets, but that's fine. Partial z, partial y, e to the x cos y. And then partial y, partial s, 2st. So for now, I'm just going to leave it exactly like this. You can obviously plug in x and y equal to st squared and y is equal to s squared t respectively if you want. But for now, I'm just trying to get you, or try to get an example across with just making use of it. Okay, and then next we still need partial z, partial t. So again, writing out the formula, partial z, partial x, partial t, plus partial z, partial y, times partial y, partial t. Okay, similar idea, we're just going to repeat what we did over here, compute the partials again. So, or we can actually reuse some of it. So we already have partial z, partial x, partial z, partial y. So what we only need now is partial x, partial t, and partial y, partial t. So these two over here. Partial x, partial t. So again, just looking at x, taking the derivative of this with respect to t now. So you have 2t times s, so 2st. And then partial y, partial t. Here, again, now t is a variable, so you're just left with s squared. Okay, and again, plugging these corresponding values in. Here, partial z, partial x, again, we know is just e to the x sine y. Partial x, partial t is 2st. Partial z, partial y, we know is e to the x cos y. And then partial y, partial t, we know is s squared. And similar to before, you can definitely plug in x and y with their corresponding representation using s and t into these equations here, but it doesn't really matter at the end. The point is, this is how you use chain rule, or the second case at least. So you also have the nth case where, again, you can imagine where x and y, for example, they both depend on n many variables. And then from there, you're kind of just repeating this branching kind of scenario. But yeah, thank you for watching.